Hello guys, let's prove this limit identity in three different ways. The calculus way, the algebraic way, and the circular way. Now, let's start off with the calculus one. Here, we have log over here, or ln, and we can use a log property to somehow prove this limit over here. So, the property we're going to be needing is the power property. So, ln of x to the power n will be n into ln x. So the power will come out. But in this case, we see that inside of the ln, we don't have any power. So what we're going to do is put the power inside the log. We see we have ln 1 plus x by x. So this I'm going to write as 1 by x into ln 1 plus x. And see this 1 by x acts as this n over here, and in the next step we can put that as a power over here. So we have ln 1 plus x to the power 1 by x, and you can actually do this directly. So before that, limit can actually go inside of the log because of the limit property. So this becomes ln of x limit 0 1 plus x 1 by x. Now, inside of the log, this limit kind of seems very familiar. Well, this is in fact equals to e. So the real definition or the famous definition is n limit infinity 1 plus 1 by n to the power of n. And what you can do is a quick substitution. Let n equals to 1 by u, and when n approaches infinity, u approaches to 0. And here just replace everything. So u approaches to 0, 1 plus 1 by n will be just u, and n will be 1 by u. And as you can see, this u is just a dummy variable because this is just in fact just a number, and it really doesn't matter if it's u, n, m or x. So we have ln e, which is 1. So there is the calculus way, and let's move on to the algebraic way. Now, for the algebraic way, we kind of have to go and look at the log by itself. We have to see how we can make the log into some kind of a polynomial function, some recurring pattern, a series. So, which means that we have to ask ourselves how we can expand this. But luckily, there is a strict and straightforward expansion of ln 1 plus x. So I'm going to write it right here. ln 1 plus x is equals to x minus x squared by 2 plus x cubed by 3 minus x to the power 4 by 4 plus and so on. And you can put this expansion right over here. So this becomes x minus x squared by 2 plus x cubed by 3 and so on, whole divided by x. And in the next step, just divide by x. So this becomes 1, this becomes x by 2, that becomes x squared by 3, x cubed by 4 and so on. And simply put the limit in, and what you'll get is 1 minus 0 by 2 plus 0 square by 3, and as you can see, all of the terms will just be 0. So in the end, you'll just get 1. Now let's move on to the circular way. So we're going to do the circular way, which is just simply using L'Hospital's rule to solve this limit. Now, I've named it the circular way because if you use derivatives to solve a limit identity, well, derivative just comes from the first principle, which is just limits. So you're using derivatives which comes from limits to prove limits, which doesn't make sense, and that is called the illogical proof known as circular reasoning. So I named it circular, and here quickly, this is the L'Hospital's rule. As x approaches to some number a, f of x by g of x, if it's in the form of 0 by 0 or infinity by infinity, then this limit is equals to x approaches a, the derivative of f of x by the derivative of g of x, so long as the derivative of g of x isn't equals to 0. So let's just quickly prove this over here. So this is equals to x limit 0, and you have to make sure it's 0. So if you put 0 over here, you get ln 1 by 0, ln 1 is 0, 0 by 0. So using L'Hospital's rule, the derivative of ln 1 plus x is 1 by 1 plus x into the inside, which will just be 1, whole by derivative of x is just 1. So you'll have 1 by 1 plus x, and simply put the limit in. You'll get 1 by 1 plus 0, which is just 1. So the most popular way, or the most conventional way, is the calculus way. And if you want to, you can also use the algebraic way to prove this identity over here, but do not do this, as it's a circular reasoning and the proof doesn't really work. But if you want to, you can. So if you learn something new, please like and subscribe. Thank you.